Hi, good morning everybody. Let's crack management exams. Join Unacademy, India's largest learning platform, and get the best possible material to prepare for CAT and all other management exams. My name is Anand Venkatesan and I'm an educator with Unacademy. I did my engineering from the IIT Vellore and then did my postgrad from IIM Bangalore. It's been an interesting journey. I've worked for about 4 years in the sales and marketing vertical. This was with ITC Limited. Had a wonderful experience. Had exposure to distribution, sales and distribution, marketing and marketing research. And I guess somewhere at the end of it, I decided that the passion area for me was going to be different. And so for the last decade or so, I've been training students for a variety of management exams. These include the CAT, the GMAT, the XAT, IFT, and PAT, you name it. And I've helped thousands of students to clear these management exams. Okay, so that was about myself. Let me also tell you about the Unacademy platform. I'm sure that some of you guys are probably seeing this for the first time. So I'd encourage you to try out, try visiting the Unacademy platform. Just download the app and try and see what it has on offer for the CAT. And to give you a brief glimpse of that, well, what do you need for CAT? You need you need a mentor, somebody who can guide you, somebody who understands their respective subject, and that's one of the things that Unacademy is really good at, because on the Unacademy app you have thousands of these educators who conduct classes, and you get to choose whom you want to study from. These educators can conduct live classes, quizzes and tests, and so there is a great degree of interaction that happens on the platforms. And finally, all of these are woven into structured courses, batches which begin on almost a regular basis. And I think the fact that it's online means that you get unlimited access to it, which is not restricted to a particular faculty or a particular batch, but you get to choose. You can choose multiple teachers, trainers, faculty members, whom we call educators, and you can choose to study at any time, anywhere, and that's unlimited access to all lectures, whether they are live or whether they are in the recorded form. I told you get to choose faculty members, so there are many countless educators on the platform who are their respective subject matter experts. So I think flexibility is the key here. You get to choose your favorite teacher. Most classroom programs probably give you something called a demo class, but sure, everything is a demo, everything is a trial, because when you start on the app, you can attend one of the special classes. What we call as special classes are essentially live lectures, demo lectures, and so you attend live lectures in special classes, experience the platform, and then graduate to Plus. And Plus is where the real sort of learning goes on. Here's where teachers run structured courses, and learners then choose to join these courses, and so you get to decide which teacher you would like to, which educator you would like to study from, and it's completely democratic in that sense. These lectures that I talked about go live, Plus lectures go live on a regular basis, right? You get to choose which faculty you want to study from, and once you do that, on almost a daily level, on almost daily basis, you have many such educators who take live classes. On the Plus, once you subscribe to one of the Plus offerings, you can study with a batch which is regular, which can cater to your specific needs, right? And I mean specific in the sense of, if you're a beginner, if you're starting your preparation now, then you probably want to join a basic course. But if you're somebody who's already been preparing for some time, then you probably need, you don't need basic hand holding, but you need advanced techniques, advanced methods, tougher problem types, and more practice. and that's something that another batch would offer, right? So a different batch would offer. So what I'm trying to say is that you get flexibility. You can choose whom to study from. You can choose which batch to study from. You can choose what time you want to study. So there's this flexibility which is built into the DNA of the Unacademy course or the Unacademy app. Well, I talked about Plus. I talked about the flexibility that it gives you. There is much more on offer when it comes to Plus, but for now I'm going to quickly tell you about the various available subscription plans. You have plans that go all the way from 1 year, 1 month to almost 2 years. So I think there is a dilemma which course will be ideally suited, and my 2 pence on that would be that it's always better to take a long-term view of your preparation. So even if you're giving this year's CAT, then bear in mind that you're actually preparing all the way till the month of April, because while the CAT exam finishes in November, the XAT happens in January, and in fact the IM calls, when they come out, PI and WAT rounds happen in the month of February and March, in fact even all the way into April. So it's quite likely that you'll be preparing for one aspect or the other all the way till April or so. So for that reason I should think that a 12-month plan is, the 12 months duration is ideally suited. But if you're preparing for next year, then probably a 24-month plan is what you should be considering. And you can see that there is a very marginal difference when it comes to the pricing of these three durations, right? So there's a very small additional cost associated with it, but the benefits are actually unlimited and infinite, because daily, in fact, new educators join the platform, and I'm sure by the time the PIWAT rounds happen, you will get access to different people from different contexts who will pose different kinds of questions, and your improvement is almost a foregone conclusion, because once you have these best trainers conducting classes, I think it's just a matter of time and effort for you to sort of create an impact in your essays and in your interviews. So yeah, choose early and choose well, and when you do, then make sure that you use my subscription code, that's AV01, when you subscribe for one of the Plus courses. Make sure that you use the code AV01. That gives you a 10% discount on any subscription plan. So I think it's something you should remember, and it's easy. It's my first name, last name, AV, Anand Venkateshan, followed by 01. Right, on that note, we'll come to the agenda for today's session. Today's a marathon session that we'll cover a very important topic for the CAT, which is logarithms and exponents. So we look at logs and exponents in detail. We try and build in a lot of practice towards this particular topic. Here's the agenda for the session. We'll learn about logarithms, the basics of logarithms, and also the properties that are associated with logs. We'll try and get a flavor of the kind of questions that come from this topic, because if you look at past editions of the CAT, whether it's the recent past, maybe the last 2 to 3 years, or even more in the past, and one thing that strikes you is that logs seem to be one of the favorite topics as far as CAT examiners go. So there's almost near certainty that 2 to 3 questions will come from the topic that we are going to discuss today, logarithms and exponents. So there's this is going to be imagine that 2 to 3 questions is almost 10% of your CAT paper. So one lecture today can actually change your fortunes in the CAT. It can actually make you good at logarithms, give you a basic primer on logarithms, and take you one step closer to cracking, a sufficiently large number of questions in the exam. So from that perspective, I think it's it's a very important lecture. And once you've taken a look at logs, we'll also recap what we know about exponents. Exponents is also an important topic. It's a related topic anyhow when it comes to logs and exponents. They're almost similar functions that have a similar nature. In fact, one is actually the inverse of the other. So that's what we cover today, and we'll try and look at problems on each one of these. Alright, so let's get into the session itself. We'll start with understanding what a logarithm is. So a logarithm is typically represented in this form, right? Log of x, and there is a subscript here which is a. So what exactly is the log of a? Well, the logarithm of any number x is defined as, this is a simplistic way of saying it. What power of the base a will give me the value of x? I take a and I raise it to a certain power, and what power must I raise it to so that I get the value of x? That's what a logarithm means, right? So for example, if you know that by raising 2 to the 4th power I get 16, I could represent this exponential relationship as a logarithmic expression by saying log of 16 in the base 2 is actually equal to 4. Yeah? So what power of 2 generates the number 16? Well, the 4th power. Or if I extend that logic, if I take other examples, so what power of 3, what is log 3 in the base, what is log 9 in the base 3? So you are asking yourself, what power of 3 makes 9? And you immediately get the answer saying, oh, that's the 2nd power, and that's logarithms, right? Or let's say what is log of 0.1, let's say 0.1 in the base 10, right? So you are asking yourself, what power of 10 makes 0.01? And if you write 0.01 as 1 by 100, then you know that this is 1 by 10 square, or 10 to the power minus 2. So what power of 10 makes 1 by 100? Makes 10 power, makes 0.01. That's negative 2, right? So that's the understanding you need to have about what a logarithm is. It describes what power of the base generates the value of x, So you can see even from the examples that I've given you that the logarithm is very, very similar. It actually is one and the same as the exponential function, a to the power something. So they're quite closely related to each other. We will keep that theme going, and this understanding is also something that we should understand as a property, because what we are doing here is essentially something called an anti-log. We are inverting the function. We are inverting the function here, right? And we'll talk about this in just a bit. Moving on from this point, right? So to elaborate what I mean by inverting the function, right? So what does log I is equal to log of x mean? It means what power of a makes x, and the answer is y, which basically means that the yth power of a would equal x, and that's what you get. And this operation is what I like to call as the anti-log operation, right? You can be given an expression, and you can start with this expression, and then you can convert it into one that does not contain a log, that in fact contains the inverse of the log, that's the exponent, right? So that operation is called the antilog, right? And so an antilog would mean that you take the base and you raise it to the value of the log, and that would then be equal to what we have inside x. Right? So like I said, it's the inverse of the logarithmic function, and that's the way that you should understand it. Obviously, we'll quickly also look at the various parts of the logarithmic function. A is called the base. A remains the base for both the inverse and the logarithmic, both the logarithmic function and the exponential function. So I understand that as base, and x is what we call as the radicand. Right? X is called the radicand of this logarithmic function, and so those are the two parts, and y itself will be the logarithm. So there are two parts to the logarithmic function, the base and the radicand, a and x respectively. Right. Let's talk about some basic rules, some ground rules when we are dealing with the logarithmic function. So there are some limitations to when the logarithmic function or the logarithm is itself defined or exists. First and foremost, the base and the radicand must always be positive. Right? So nothing in the logarithmic function can be negative. Remember, when I write log of x in the base a, then I mean neither this nor this can be negative. They cannot, in fact they must be positive. Forget about being negative, they must both be positive. They can't even become zero. Neither can the base be zero nor can the radicand be zero. They must be or negative. They must be positive in all cases. Only then will the logarithm exist. In fact, since we convert it into an exponential function, it will cease to be a function if the base were equal to 1. Because if the base is 1, then think about what the exponent would be. If the base is 1, then you are talking about the logarithm as log of x in the base 1 as equal to y, but then that would also imply that on applying the antilog operation, x must equal 1 to the power of y, and that doesn't make any sense, because 1 to the power something is always 1, which means irrespective of x, irrespective of y, the value of the radicand will always be 1, and that doesn't make sense. So for that reason, you disallow the base from being ever equal to 1. Alright, and then we come to common logarithms that we tend to use either in applications or in fact in practice questions. So the two logarithms that you might come across would be in fact what we call as the common and natural logarithms. Both the common log and the natural log is something that you will come across and you will use. So the common logarithm, the one that we use in our life when we deal with logarithms, is one which has a base of 10. So this is one of the most common logarithms, which is raised to the base of 10, and so you can and you notice what the notation for base 10. What I've done here is that I have not written the base. So if ever you write log of x without the base, then it is automatically understood that this must be a logarithm in the base of 10. Right? Okay. But why 10? Why is it common to use the base 10? We deal with, remember, the decimal system. So 10 is a crucial sort of number in the decimal system, because 10 denotes the number of digits that we have. 10 denotes in fact the place values for every single digit in the number system, in the decimal system. So 10 is one of the most commonly used bases when it comes to logs. And there's an interesting fact again if you think about it. So if I consider a logarithm in the base 10, right? So what power of, so let's say I'm talking about log of 100, then I get what power of 10 makes 100? The second power. What power of 10 makes 1000? I get the third power. What power of 10 in fact makes 10? That will be the first power, right? So while we are talking about power, the logarithm also tells you, in a sense, the number of digits in the number, because if a logarithm is equal to 10, if the radicand is equal to 10, then the value will any logarithm, by the way, let me sort of recap that, rewind and rephrase that. So any logarithm which lies between 1 and 2 will represent a number from 10 to 99. Any logarithm which lies in the range of 1 to 2 will be a number from 10 to 99, which is like a 2-digit number. Similarly, any logarithm that lies in the range of 2 to 3, 2, 2.1, 2.2, 2.3, 2.9, the radicand will lie in the range of 100 to 1000, which means we're talking about 3-digit numbers. So in one sense, considering the base 10 will give you, the logarithm value will also give you an understanding of how many digits the number has, because if it has n digits, then its value will be between n minus 1 and n, right? So if I have a number which has, let's say, 7 digits, right? If I have a number which has 7 digits, then I will know that the logarithm will lie between, log of n will lie between 6 and 7. Right? It can't be equal to 7, but it can definitely be 6 if it is a 7-digit number. So I think that is a very, very useful point to remember. Number of digits are very, very close to the natural logarithms. To the common logarithms. Common logs are very, very closely linked to common logs. But natural logs, are what occur in nature. Right? Natural logs are most commonly occurring in nature. You have these, you consider the base as e, one of the most common mathematical constants, which is equal to 2.71. Yeah, so if you studied calculus sometime in school, then you'll remember e power x as opposed to a to the power of x, and clearly e is a very specific value. It's a mathematical constant, and so e to the power x will probably generate a lot of these sequences that you observe in nature around you. Patterns of flowers and the way colors are distributed. A lot of these things are actually indexed to infinite series, infinite sequences, and e power x, e itself, the number e and pi, are two very, very intricate sort of ingredients of that pattern. So natural logs is what you call them, and since you call log with the base of e as a natural logarithm, you in fact can write it as ln, log, which is natural. So ln of x will, if you come across that written, then you should be able to understand that we're talking about the natural logarithm here, which has the base as e. Right. So I hope that we understand logarithms a little more. I think a question that usually comes to mind when you start to study logarithms is, okay, I think I'm starting to understand how the logarithm works, But then why have one at all? Why have something called a logarithmic function which measures the power, so to say, right? So why have one at all? Well, when we deal with math and it gets into correlations and predictive algorithms and in fact even data science, it turns out that one of the needs that we have is to be able to explain different kind of patterns, and these patterns involve sometimes numbers which have very, very different scales. They occur, the range of values that they occur in is very, very large, and you need to do better than polynomials in order to be able to, or functions to be able to explain their behavior. So it turns out that the logarithm is useful if you're studying science, or if you're studying, if you're dealing in pattern recognition, or in fact there is one application of the logarithm which every one of you will actually know. Logs help us understand earthquakes. They help us understand what the magnitude of an earthquake is, because if you remember, how do you measure the magnitude of an earthquake? There is something called the Richter scale, which has been invented, and the Richter scale tells you the magnitude of the earthquake that occurred. Right? What is magnitude? So it's one magnitude would be one variable or one sort of descriptor of the earthquake, which basically defines how strong or powerful an earthquake was. Right? Was it a mild one, or was it a very, very strong one? And that would be measured as magnitude. So that's what the magnitude tells us. So an earthquake which has a very high magnitude, immediately you can perceive that its after effects, its destruction and so on and so forth would be much more severe. Okay, this is stuff we know, right? We've studied about Richter scale in school, I'm sure, and every time you feel a tremor, you go online or you watch the television channels and they give you this number. They tell you that this earthquake had a magnitude of so and so on the Richter scale. Well, we've all heard about it, but what we don't know is that the Richter scale is in fact a common logarithm. The Richter scale in fact does not measure the logarithm itself, it measures actually log of m. Is what you get on the Richter scale, right? Now, how does that help me understand earthquakes better? Well, if you think about it, usually you hear about earthquakes having magnitudes of these are magnitudes which are always less than 10. And so if I want to compare an earthquake of magnitude, let's say 5 versus another earthquake of magnitude 7, right? In itself 5 doesn't seem very, very small, 7 doesn't seem very, very large in compared to a magnitude 5 earthquake, right? So at best you'd say maybe it's 20%, it's 40% more. Yeah. Okay. So this seems to indicate that the magnitude is just 40% more, right? It's going to be only 40% more powerful than a magnitude 5 earthquake. But no, since this is a Richter scale, the magnitude 5 does not refer to the intensity or the magnitude itself, but rather its power when you raise it to the power of 10, the base of 10, which means you're actually wanting to compare a magnitude of 10 to the power 5 versus a magnitude of 10 to the power 7. Right? Let me write that out for you. Right? Magnitude 5 would mean 1 lakh, 1 followed by 5 zeros, but magnitude 7 would be 1 followed by 7 zeros. just like a crore versus a lakh. So is a crore more than a lakh? Yeah, it's 100 times. So it so happens that the magnitude of what seems like an innocuous number, magnitude 7, is actually 100 times the severity of, it will have 100 times the severity and the destructive power of a magnitude 5 earthquake, right? So the next time you read about an earthquake, I certainly hope you keep that in mind. Alright, so I mean, what I'm trying to do is I'm also trying to give you a flavor of why logs are important, why they are used worldwide. So anything that sort of lies in this very vast range, from the very, very small values to the very, very large values, and all these values are very, very commonly occurring, then putting them on a normal linear scale, or even a quadratic or a polynomial scale, might not be doing justice to the variable itself that you're measuring. So a better approach is to put it on a logarithmic scale, is to measure not the value itself, but what power it would take when raised to the power of, when expressed as a power of 10. Right, now the lecture will move on into the properties of logarithms, right? Can we understand properties? Can we look at some of the basics, basic properties of logarithms? And that these are properties are very, very important. First and foremost is the basic property, is what we understand as the anti-log operation. But sure, you should know how to do an anti-log, but always keep in mind that the description of a logarithm is always what power of a. What power of a makes x. That's an understanding that you should always keep in your mind. But yeah, obviously it's not always convenient to think about it that way. It can tend to be a little confusing. So even if you do get confused, remember what the anti-log operation is. And again, that's a simple operation, because all you need to remember is anti-log is an exponent. Right? If I remember this and I look at log of m in the base a is n, right? So you're thinking, okay, I want to rewrite this, but I want to rewrite it as an exponent. So a to the power something is what I want to put. Well, if the log has m in the base a, then exponent also cannot have m in the base a. So you'll choose n here. Right? So you'll say, okay, if m does not make sense there, then we'll use the value n, and this would then be equal to the missing number, missing value, which is the radicand m. Right? So you guys should be comfortable performing the anti-log operation. उसको inverse करना आप लोगों को आना चाहिए, because that's actually very simple. It's very simple, and you won't make mistakes if you practice doing this on a regular basis. Every time you see a log, you should be able to visualize its anti-log, its exponential form. Right, sorry, let me clear up the screen so you guys can see the next property. So what that means is that if you understand the basic definition of a logarithm, then you'll also understand some of these applications of this property. So thus, when you take logarithm of a in itself, then you're saying what power of a makes a? Well, first power. Similarly, what power of a makes a power n? Well, the nth power. Right? So if you don't understand that, then try to take let's say you didn't know that this is n. Right? Let's say that you thought this was y. Then you'd say take an anti-log. Take an anti-log, and what will that do? It will mean that a raised to the power this value y would be equal to a to the power n, and you can see that two exponents with the same base clearly means that the power should be equal, right? So the logarithm itself must equal n. moving on. What power of the base a gives you 1? What power of a gives you this value 1? Right? Always when you are evaluating this, think about the radicand, not about the log. That, when you evaluate as what power makes this, right? So you're only focusing on base and the radicand. You're not bothered about the value of the logarithm. But when you take an anti-log, then you swap, you swap the radicand with the logarithm value, right? So the two, while they essentially explain the same thing about a logarithm, but they do so in fundamentally different ways. Right. So these were basic properties. Now, one of the most commonly used properties, right? If you get a question from logs, well, the chances are that you're going to use this addition property of logarithm. So the addition property of logarithm says if you add two logs, their radicands will get multiplied as long as the two logarithms that you're adding have the same base. So when you add two logs in the same base, their radicands will multiply. If you subtract two logs in the same base, then their radicands will get divided. Right? And this is a property that you should be able to use both ways, from left to right as well as from right to left. Right? So either a difference as the product of radicands, or a product of radicands means that you can split it into two different logs which are simply being added. Yeah. So for example, if I say, okay, I know log 2 is 0.3 and log 3 is 0.4, let's take some values. Then what can you say about log 6? You'll say no problem, log 6 is nothing but log of 2 into 3. Right? And when two things are getting multiplied, the logarithm will end up adding those two things. So log 2 plus log 3. What would that be? Log 2 is 0.3 and log 4 is, let's say, 0.4, and so this will become 0.7. So there you go, that's the value of log 6. So if ever you can create something by multiplying the radicands, then their logarithms will get added. Similarly, if you were to divide two logarithms, two radicands at least, then you can split that into two logarithms which will get subtracted. Right? So, think about it. So let's say I want, given these two, I want the value of 1.5. What is log 1.5? You'll say no problem. This is log of 3 by 2 in the base of 10, right? I've not written the base, so all of these have the base as 10. So what is log 1.5? That's log 3 by 2. But log of a by b or log of m by n is inherently log 3 minus log 2. I can take a division inside the logarithm and convert it into a subtraction of two different logs. And so my answer becomes 0.4 minus 0.3. That's 0.1. Yeah. So again, very very simple sort of applications. This type के application, this type के properties are very useful, right? You're probably thinking this one is easy. Maybe logs is harder when we go deeper into it. Well, to be honest, most logarithm questions will be based on just these 2-3 properties, maybe a few others, maybe one or two others. But it's a very sort of small list of properties that we will use, literally 5, maybe 6 properties. So I genuinely feel that even if you've not studied math, after school, and you're really serious about the cat, then logs is important. And I also believe logs is not very hard, because if there are only, because if the log is nothing different from an exponent, you shouldn't have problems understanding it. and the the properties of logarithms number in literally single digits, maybe not even 9 or so, it's only 5 or 6. So if you have only these number of properties, then how hard can it be to know those properties and to be able to apply it in problems? Because then chances are that if you have a limited set of properties, then there's only as much variation that the problem can expect. So keep that in mind, and I'll continue on with quickly telling you about the properties of logs. I'll move on to the next one. Here you have logarithm of an exponent, m to the power of n, right? What is the log of m power n? So it turns out when it's m power n, that the power n will actually come outside the log. It will become n times the log of m. Why is that? Well, this property is actually a consequence of the addition property, right? Because think about it, what will this be? This is nothing but log of m into m into m. If you think about explaining this off, log of m multiplied with itself n times, many times, would make the radicand, right? But we know that the addition rule of logarithm says that if you have a log where the radicand has a product, then you can split this into many logs, each of which contain the value m, right? So I can say log m in the base a plus another log m also in the base a, and so on and so forth till I end up doing n times. Why n times? Because if you're multiplying it n times, then you can keep on splitting it into terms which get added, and you'll end up getting n terms such as those. So, and you can see that if it is log m plus log m n times, it should be n times the log of m, and when it's taken in the base of a. So this is a useful property. You should definitely remember it. You should definitely understand it. It's derived from your basic addition property. And if you remember, if you go back to the initial part where I talked about logs, then I said what is log 16 in the base 2? So next time you should directly be able to see this as log 2 to the power 4. And when it's an exponent, the power comes out. So I'll write this as 4 times log 2 in the base 2. But then when the base and the radicand are the same, the logarithm is 1. So this becomes 4 into 1, 4. So what power of the base makes the radicand? That's hence to log 2 in the base of 2 would be necessarily 1. Quickly sort of erase all of this, yeah. But what if the exponent, what if you have something to the power of something else, not in the radicand, but rather in the base? What if the base itself is not, it's not a, it's actually an exponent in the base of n? What if you have that? Well, this power also comes out, but the difference would be when it's the logarithm, when it's a radicand, the power comes out in the numerator. When the power exists in the base, then the power comes out in the denominator, right? So you can see if it's a to the power n, then the nth power is occurring in the base, and if there is an nth power in the base, I can take that n out. So you take n outside, it will become n 1 by n though, because it comes out from the base, not from the radicand. So you will end up getting this 1 by n times log m, right? And that's because the base had a, the base is also changed. If you notice, the base has become a. Right? So that's a useful property, how to deal with logarithms that contain powers, and such powers are contained either in the radicand or in the base. So when it's contained in the radicand, you take that out in the numerator, but when it's contained in the base, then you can extract it and place it in the denominator. And then comes one of, again, a very, very important property. So we've learned how to multiply logs and subdivide logs, or the addition rule or the subtraction rule. I think another important rule is the change of base. What if you have a base you can't really understand, or you can't really imagine the properties? Or what if you wanted to change the base for some reason, for some higher reason? Well, you can change the base. In fact, here's how the change of base formula looks like. You can see that when I started off, I had a log, I had a logarithm in the base of a. And if I want to change the base of this logarithm, right, I don't like a, let's say I want to use the base as b. So the logarithm, the change of base allows me to do that. It says, okay, no problem. When you want to change the base, you convert the logarithm into a division of logs, right? And there are only two things that we know that occur in a log, right? You're either talking about the radicand x, or we're talking the base a, or in this case a power n maybe. So when you are converting log of x in the base a, so you want to change the base, then you say it should be the fraction that is represented by log x by log a, right? And log x as well as log a can both take any base that you want to choose, right? So the matter is entirely in your hands on how you want to watch these, how you want to change the base of a logarithm. Right? Log x in the base, log x divided by log a. So for example, if you have log of, let's say, 2 in the base 16, then you'd say, okay, since the power, 16 is a power of 2, so this is 2 to the power 4, so I can take the 4 outside, only it will come in the denominator, and this will then convert into log of 2 in the base 2, right? And clearly, the first power of 2 is 2, so this is like 1 by 4 into 1. Yeah. But what about let's say log of 16 in the base 8? What about log of 16 in the base of 8? Because if you start to apply the basic property of a logarithm, then the question you are asking yourself is, what power of 8 makes 16? But that doesn't sound right? Because 16 is not a power of 8. So what do you mean, what power? Right? I can't at least use the traditional calculator to find out the answer for me. So, but you can still, find its value. How do you do that? So log 16 in the base 8 can also be written as log 16 by log 8. Right? And obviously the bases are 1. And in fact, don't take the base as 10. You can choose any base you want, but if you observe 16 and 8, you know that both of them are powers of 2. Right? So if I write log 16 in the base 8 as log 16 by log 8, when both of these are expressed in the base 2, now if you use the basic definition of a logarithm, what power of 2 makes 16 in the numerator? Well, the fourth power of 2. Similarly, what power of 2 makes 8? What you can see in the denominator is 2 to the power 3 is 8, which means the logarithm itself will be 3. So my answer is that it's a constant, 4 by 3. Even though it contains many logs to begin with, even variables to begin with, but at some point your house will get sacked. Alright, so I hope the change of base property is clear. I can probably give you one more example for that. Supposing I may clear this place up. So supposing I want the log of 243 in the base 81. Don't say I don't know, right? You should be able to observe. Observations are very important in the CAT. You need to observe the nuance within the problem. So if this is occurring in an expression, then you should start thinking, okay, what do I know about 243 and 81? Right? What do I know about them? Both of them are powers of 3. So it basically the question means what power of 8 makes, what power of 81 makes the number equal to 71. Well, if I know that, then I can apply change of base and I can write this as log 243 divided by log 81. And I can now choose any base I want. Right? So let's say I choose the base as 3, because both 243 and 81 are base, are powers of 3. So I can choose the base as 3. And if I do that, and you go back and circle back to the original definition, numerator is log 243 in the base 3. So what power of 3 makes 243? You can either think on those lines, or you can, write 243 itself as 3 to the power 5. Right. Similarly, what is log of 81 in the base 8? That's like log in the base 3, of 81, which is 3 to the power 4. Right. So we get a fixed value 5 divided by 4, which clearly would be the value of log 243 in the base 8. So I hope that you guys got a flavor of how logarithms work, what the basic properties are. These are the ones that I can firmly say, I can say with absolute confidence, these are the properties which get used on 99% of the problems. But then, which means there is something which is sort of an exception, right? So it's a very simple expression, x to the power of log y. It's the only expression which contains logs and exponents in the same term. Can you see this? X raised to the power of logarithm. Right? So the property basically says that if you're expressing an exponent with a logarithmic power, then you can always stagnate the student. You can always, in a sense, you can always swap x and y. Right? That's the way the property works. If you have an exponent contained in the log, then the base and the radical for the logarithm and the exponent respectively can be swapped. Right? So which means x to the power log y can be written as y to the power log x, as long as they are in the same same base. But then this is a slightly obscure property, because this property is not as widely used, as commonly used as the other properties that we just discussed. Alright, now that we've looked at the basic properties, a quick recap. You need to make a mental note of this. So what properties did we study? We learnt about how to add logs, how to subtract logs, how to do n times a logarithm, add means you multiply the radicand, subtract means you divide by the radicand. And if you are doing n times the logarithm, then you know that the radicand becomes log of x power n. Right? So you know how to take powers outside the logarithm or outside of the base. And finally, we've learnt about changing the base itself, followed by this attempt to sort of discuss the basics and get into some problem types. So here's the first question that we discussed today. Right? If log of x is equal to -2, then what is x equal to? Well, if you simply perform the anti-log operation, what will you get? 3 raised to the power, the other number minus 2 should be equal to y, which means y will be 1 by 9. Sorry, this is not y, this is x. So x is 1 by 9. Let's look at another question. Whoa, seems like such a big expression, but you should start noticing these things in the expression. You can see that there are 4 logarithms. All 4 logarithms have the same base 10 and they're being added. So immediately in my mind I should be able to see the addition rule of a logarithm says that when you're adding many logs in the same base, then you could also, instead of adding them, you could also multiply them inside the radicand. Right? So I could say this should be equal to log in the base 10 of multiply whichever is getting added, that's 36 upon 91 into 119 upon 91. So it should be 36 by 51 into 109 by 91. But then when you subtract, you don't multiply, you actually divide. So you say divide by 13 by 32 and also divide by 64 by 39. Right? So if you look at this expression, I can probably simplify it. This becomes a question actually from bod mass in a sense. So 36 by 51 into 119 by 91, and let's invert this and put it as a multiplication, so that becomes 32 by 13 and finally 39 by 64. So 13 into 3 is 39, 32 into 2 is 64, (17) into 3 is 51, 17 into 7 is 119, 7 into 13 is 91, and obviously 3 into 2 is 6, 6 times 6 is 49, sorry, 6 times 6 is 36. So what does this become? This is all there inside the logarithm. So the logarithm in the base 10 should then be equal to what is left, log in the base 10, and then you have 6 in the numerator maybe. Yeah, I don't think anything else is really cancelling out here. So it reduces basically into log 18 by 13. Alright, move on to the next question here. Find the value of the log shown here on the screen. Find the value of log 32 when it's taken in the base of the square root of 2. So what I can do is I can assume this, in fact I can use the property directly. That's one way of doing it. This is log 32, square root is the base raised to the power 1 by 2. So root of a will be 2 to the power 1 by 2. So this becomes log of, but then I know the property that when the base gets square rooted or it's raised to a certain power, the logarithm value will change because of that. So and you know that property is that when the base of the logarithm has a power, you can bring that power out only in the denominator. So I'll write this as 1 upon half into log of 32 in the base 2. And let's think about this one number first. Obviously 1 upon half will become 2 times what power of 2 makes 32? The fifth power. Right? So that's my answer. 2 into 5, 10. The value of this logarithm is equal to 10. Hope that's clear to you. Alright, at this point, guys, I'm going to take a short break. Give me a couple of minutes or so. I will leave you with a question. Right? I'm going to leave you with this question. What is the logarithm of 0.0625 to the base 2? And I'll join you back in 2 minutes. I want you guys to try this out, and I'll discuss the solutions with you very, very shortly. So see you on the other side of this very short break. So I hope that you guys managed to crack this question in the meantime. Sorry for that. So a couple of questions that we want to take a look at. First one, find the value of log of 7 in the base of 343. Right? Again, we can use that property log. This is log of 7, and you should notice that 343 is in fact 7 into 7 into 7. 7 cube is what 343 is. So this logarithm is log of 7 in the base of 7 cube. And when the base has an exponent, when the base itself has a power, that power will come out in the denominator. So I can write this as log of 1/3 of log 7 in the base 7. And when the base and the radicand are equal, the logarithm is equal to 1. So this becomes 1/3. Yeah, very, very simple. Okay, here the question spells it out in words. I need to express this as a logarithm. So we want log of 0.0625 in the base 2, right? So you first look at 0.0625, right? So you could write this as 625 by, how many zeros would I need to put? 4 zeros, so that becomes 10,000. And then I could divide, right? I could divide by 25. 25 into 2 is 50. In fact, 25 square is 625, and 25 into 4 is 100, so 400. And again, cancelling it out, I'll get 25 ones are 25. That leaves me with 150. So 25, 6 are 150, which means that 0.0625 is in fact 1/16, right? So this basically becomes log of this becomes log of 1/16 when raised to the base of, when expressed as a log in the base of 2. So what power of 2 makes 1 by 16? You could either directly know that this is be minus 4, but if you don't understand this, then you'll think, okay, let's say log of 1 by 16 in the base of 2 is equal to y. Then taking an anti-log operation, performing the anti-log operation, you'd get that, the power of, you want to express it as an exponent in the base of 2 to the power y would then be equal to 1 by 16, which itself is 2 to the power minus 4. So y must equal minus 4, right? So you can see that, in this manner you can take a very simple expression and you can evaluate it accordingly. Okay, here's a different kind of question. So far we were dealing with problems where I wanted to calculate the value of a logarithm when the base or the exponent has a certain power. Now we shake things up a little. We are given two logarithmic expressions, and the question says find the relationship between the radicands p and q, right? So let me write these. Log p in the base 8 is 25, and let's, when we deal with logarithms, then the anti-log is a good idea. Is always a good idea. So since we want p, we'll get that from the anti-log operation. So the base 8, when raised to this power 25 would result in p, right? So that's what the anti-log operation will tell me, which basically means that p would be equal to 8 to the power 25, but 8 itself is 2 cube. So this is like 2 cube to the power 25. That's 2 to the power, when you have exponents, you in the same base, you multiply their power. So this becomes 2 raised to the power 3 into 25. That's 2 to the power 75. Okay, that completes my first expression. I found out the value of p, but then I want the value of p with regard to q. So let's work with the second logarithm, right? Now I have log of q in the base of 2 as equal to 5, right? Again, take an anti-log. Again, if you take an anti-log, you'd say that 2 raised to the power 5 should be equal to q. So you have q and you have p, which equals 2 to the power 75. So in order to express p in terms of q, you'd say p would also be, both are powers of 2, notice that. So you want to write this as 2 power 75 as 2 power, 75 can be written as 5 times 15, which basically, using a property of exponents, you can write this as 2 power 5 raised to the power 15, because when you raise an exponent to another power, their powers get multiplied, which means that p would be equal to 2 to the power 5, I can substitute with q, so p becomes q to the power of 15, right? And I hope that you can see what kind of manipulation you can do with logarithms. You can do with logarithmic expressions, you can combine them and express them, express a relationship between them. Alright, here's another question, right? Again, you have two logarithmic expressions that you want to sort of combine. So I'll start with this expression and I'll say, okay, let's do an anti-log on this. What will that give me? X, the base, raised to the power of the log value, that's 100, would be equal to y. So y is x to the power 100. Okay, we want the value of y, we have the value of y, but you don't know the value of x. So to calculate x, you need to work with the second expression. Take an anti-log here, and this time you work with the base of 2. So you say 2 to the power of 10 would then be equal to x. And if I take this and I substitute it there, you'd say that y would then be 2 to the power 10 raised to the power of 100, which is like 2 to the power 1000. So there you go, that's the value of y, 2 to the power of 1000. I hope you guys are finding these questions basic and you're able to appreciate that if you're comfortable with the basics, then we can then move up levels. We can move to tougher problems, harder problems. Okay, let's look at this question next, right? If, by the way, if you're watching a recording of this video, then I would really suggest that you pause the video and try this question yourself, and then watch the solution. Watch the way I solve this for you. So let's work with this, right? In the initial step, right, you can see that you have a logarithm equal to a constant, right? So in the first step, since there are 3 logarithms, you want to reduce it to, you want to remove all the logs from the operation, only then I can get the value of x. So which means I need to remove all logarithms, which means I need to do anti-log operations. So first anti-log operation will mean that the base is 2 and this is the power. So 2 to the power 1 would then be equal to the radicand, which itself is one that's composed of logs. So that would be log in the base of 3 of log x in the base of 2. So which basically gives me that log of log x is equal to 2. Taking an anti-log again, what would happen? Right? So now that would mean that the base is 3 and the power is 2. So 3 to the power 2 would then be equal to log of x in the base 2. Right? We've removed 2 logarithms. We've inverted the function into exponents. What does that give me? This gives me log of x in the base of 2 is equal to 9. Now if I want the value of x, I will take an anti-log again. But remember, this is the third anti-log operation we're performing, and in this case 2 will be raised to the 9th power. So 2 to the power 9 would then be equal to x, right? And there you go, that's the final answer. X must be equal to 2 to the power of 9. Yeah, I hope that you can see what looks like a complicated question to begin with isn't so complicated after all, because all you needed to do was apply the anti-log operation about 3 times. Let's take a look at this question, right? You have log of a sequence of numbers which are being multiplied, a large set of numbers, in fact 9 numbers that are being multiplied. Well, we'll use the property of exponents first. When you multiply exponents in the same base, it turns out that their powers get added. So which means this will become 1 plus 2 plus 3 all the way till 9. Right? That's what this gives me. And the power now contains the sum of these consecutive integers starting from 1. Right? And I hope you remember that the sum of the first n integers starting from 1 is n into n plus 1 by 2. And so this expression 1 plus 2 plus 3 all the way till 9 would then be 9 into 10 divided by 2. That's 90 by 2, which is 45. Which basically means that this will then reduce into log of 10 raised to the power 45 in the base of 10. Right? And so if I express this as y, then taking an anti-log operation here, you get 10 raised to the power y would equal the radicand, and in this case my radicand is 10 power 45. Since their bases are equal on both sides, we'll say the radicands, the powers must be as well, so y must be equal to 45. Right? And that's your final answer. So the required expression, which we denoted as y, would then equal 45. Okay, here's another question, right? Find the value of log something, 1 by 2 plus another log 1 by 3, and then there is, it seems to sort of indicate that this expression will go on. And there is a pattern that will continue. What is that pattern? You can see both the radicands have 1 followed by a fraction, and that fraction contains 1 in the numerator and an integer in the denominator, and the integer in the denominator seems to be increasing, right? So if I want to think about the terms, this would be log 1.5 plus log 1 1/3 plus log 1 1/4 and so on, till the last term. Now since it talks about 198 terms, what would the last term be? There are many ways of doing this, right? One way is to think that here my denominator is 2, here my denominator is 3, here my denominator will be 4. So the denominators increase from 2, right? So the first term contains 2, the second term contains 3, the third term contains 4, and you can see each time the term number gets incremented by 1, and that becomes my denominator, right? So if you talk about the last term, which is the 198th term, then its power should in fact be 1 more than 198, that's 199. Right? So that's one way of figuring out that this would be log 1 by 199. Alternatively, you could have also figured this out by thinking about this, the powers as nothing but a AP, nothing but an arithmetic progression. So you want the last term, which is the 198th term, but we do know the expression for the nth term of an AP, which is a plus n minus 1 into d. So here the first term a is 2. You want the value of n as 198, so n minus 1 would be 197, and the common difference here is 1, right? So if you add, you'll get 2 plus 197, that's 198. Sorry, 2 plus 197 would be 199. So there you go, that's the denominator in the last term, which is exactly what we anyway sort of figured out by common sense. Okay, so now you have the expression, you have every term. Obviously you will express this mixed fraction as a improper fraction. So 2 ones are 2 plus 1 3, so this is 3 by 2. Next one will be 3 ones are 3 plus 1 4, so this is 4 by 3. And this one will be 4 ones are 4 plus 1 5 by 4, all the way till the last term, which will be log 199 plus 1, 200 upon 199. And what happens here? Well, you're taking a number of terms, you're taking a number of logarithms and you're adding them. So what about the addition rule of logs? The addition rule of logs says that if you add number of logs, all of them in the same base, then their radicands actually get multiplied. So this becomes log, obviously the base remains 10, of 3 by 2 into 4 by 3 into 5 by 4, and this continues all the way till you reach 200. In fact, let me also write down one or two terms before the last term. So that's going to be 198 upon 197 into 199 upon 198, and finally 200 over 199. Right? And then let's see what happens. So you can see that the way the series is built, consecutive terms will have numerator cancelling out with the next denominator. Right? So 5 will also get cancelled out, and this would continue till you reach 198, which cancels out. 197 would have cancelled out with the previous one, and 199 also goes away. So what you're left with is log of 200 by 2. That's log 100 in the base of 10, right? And if you take the anti-log now, right? If you think about this as y, then taking an anti-log means 10 raised to the power y would be equal to 100, which is 10 square. And since both sides now have the same base, we can equate their powers. So y should be equal to 2. So this complicated expression contains many logarithms. In fact, 198 terms actually reduces into the very simple value, which is 2. Right? I hope that made sense to you. Let's move things ahead. What about this expression? Right now, unlike the previous question, this also has many logs being added. But unlike the previous question, here you don't have an infinite number of logarithms, you have a finite number of terms. So I need to somehow manipulate this expression, use some of the properties that we've learned. So first thing you notice is that there are plenty of additions. There are 4 logarithms which are added, right? But then, unlike the previous case, these are not just logarithms, these are multiples outside. You have these multiples which are outside every term. So what do I do with multiples. This should bring back the multiplication rule. N times log of A, or n times log of m in the base of A, would actually be equal to log of m raised to the power n. Right? The power goes out, but you could also reverse it and say when there is a constant outside, you can take that inside the log and put it in its power, put in the power of the radical. So here this becomes, the original expression would then become log, you have a 2, so no problem with this. But then the next one has 16, which will go inside, which means this becomes log of 16 by 15 raised to the power of 16. And then you have an addition of another log, you can take the power inside, this becomes 25 by 24 to the power of 12. And finally, you'd have 7 which goes inside, that's log of 81 by 80 to the power of 7. And since I have many terms that are being added, you can also write this, we can use the addition rule at this point, right? Remember the addition rule? The addition rule says that if you add two logarithms, log m plus log n, then you could actually multiply these radicals mn and express it as a singular log, as long as the bases are the same. So here all the 4 logs are common logarithms in the base of 10, which is why I chose not to write it and save myself a little bit of time. But since they all are in the base 10, I can multiply their radicals, which means this becomes log of 2 into, and now I can simplify this further. I can write this as 2 to the power 4 by 3 into 5 raised to the power of 16. I'm prime factorizing each of these, into 25 by 24 can be written as 5 square. 24 is 8 into 3, that's 2 cube into 3 raised to the 12th power. And then you multiply this with 81 by 80, that's 81 is 3 to the power of 4, and 80 is 16 into 5, that's 2 power 4 into 5 raised to the 7th power, right? So this is what I end up getting, right? I have the product of 4 different radicals, but I factorize every radical into its prime factors, right? And now I can then open up these expressions and see what happens. So first is 2 into, so 2 power 4 raised to the power 16 will be 2 power 64, but then the denominator would contain 3's, so 3 to the power 16 into 5 to the power 16. Again in the numerator, from the next term I'll have 5 to the power 2 into 12, that's 24, but the denominator will get 2 to the power 3 into 12, that's 36, into 3 to the power 12, and finally I have 3 power 4 power 7, that's 3 power 4 into 7, 28, but my denominator will also get 2 power 4 into 7, that's 28, and 5 power 7, right? And so you can see there are many such exponents inside the radical. To evaluate, you combine powers of 2 together, 3 together, and 5 together, right? So this reduces into log of what's inside the, in fact, let me write it here, right on top, which basically means that we'll get log of, what is this? So let's add all powers of 2, let's combine all powers of 2. So I have one's first power, and then I'm multiplying this with the 64th power, so I can add 64, and nothing else in the numerator. In the denominator, which means I'm dividing, so that will get subtracted. So you have 2 powers of 2, which are 36 and 28. So you can subtract these, and this gets multiplied with powers of 3. Let's do that. 28 in the numerator, 16 in the denominator, and 36. No, not 36, sorry. 16, 12, are what gets subtracted, 16 and minus 12. And finally with 5 you have 24 in the numerator, but in the denominator I have 16 which gets subtracted and 7. Right? And what happens here, right? So if you look at the power of 2, 64 minus 28 plus 36 is 64. So 64 and 64 will actually get cancelled out. You'll be left with 2. So this becomes log of 2 into, what about 3? 16 plus 12 is 28. 28 minus 28 is 0. So 3 power 0 will be 1. And finally with 5, I have 24 minus 16 plus 7, 23. So this is 24 minus 23, which is 1. So 5 power 1. So you end up getting log 10 in the base of 10. And when the base and the radicand are the same, the log value will be 1. So the final answer becomes 1. Right? It does look a little, hodgepodge. If you're watching this, then since this is the first time I showed you every single step, but if I was solving this myself, I'll probably skip a few of these intermediary steps and probably do this mentally and cut out some of these steps. So for example, I can directly start doing, since this is the sum of logs, I'll multiply 2 power 1 with this raised to the power 16, that's 2 power 4 to the power 16 divided by 3 power 16 and 5 power 16. Then multiply this with the next radicand where the power will go inside, so that will become 5 square to the power 12 divided by 3 into 8, so 3 power 12 into 2 cube to the power of 12. And finally multiply this with the final radicand, which is 84, that's 3 power 4 to the power 7 divided by 80, which is 2 power 4 power 7 into 5 power 7. Right? And if you then simplify, you can sort of see that you'll get 10. Right? If you do it this very in a short manner, you can just sort of add these powers and subtract these powers, and you'd see that 16 plus 1 17. 64 plus 1 65, minus 36 minus 28 would be 2, and similarly 3 power 16, you can subtract 28 minus 16 is 12, and 12 and 12 will cancel out. And similarly with 5 power 24 is divided by 5 power 7 and 5 power 16, that cancels out and gives you 5. Right? So this, you'll end up getting 2 into 5, which is 10, and so this becomes 1. With practice, I guess you get better at this. It, I guess, also depends on how confident you are with the methodology that you're using, and I guess that's also a quotient of how much you practice. Right? So my recommendation would be that you try this, try these kind of questions, try more problems, visit the Unacademy app, visit the Unacademy website, or download the app. And once you subscribe, there's so much practice on there. Make sure that you delve deep into many logarithmic problems involving logs. Myself, I would be conducting follow-up sessions on logarithms. So we'll explore this topic in detail. Okay, for now let's move on to the next question. If log of AB is equal to x, then what is the log of AB in the next base, in another base B, right? So what happens if you were to change the base? So you can see, since the base is changed, I need to use the property of change of base. How do I use it? Okay, let's start with the first expression. Log of AB in the base of A is equal to x, right? Which means that, and if I apply the change of base property here, you'd say you can write this as log of AB divided by log of A. And if I want to change the base, I can assume a neutral base, 10, right? Which means I can write this as log of AB, which from the addition rule, this will be log of A plus log of B, and the denominator is log of A, right? So in a sense, x equals this. So you can calculate, you can substitute this in some way. What do I substitute? If I split this, then this becomes 1 plus log b by log a as x, which means log b by log a, which basically means that log b by log a, both of them in the base 10, would have the ratio x minus 1. Alright, so let's now use it on the second logarithm. Log of, say we want to calculate this value, so I'm going to denote this value as y, and we want to find the expression for y. So let's say we want y, which is log of ab in the base b, but I can apply the change of base property. What would that tell me? That would say y should then be equal to log of a plus, I'm splitting this, so log a, in fact maybe I'll split it the next time, log ab divided by log b. Notice that I've again kept the base the same, 10. So what does this give me? This gives me again log a plus log b in the numerator, but now my denominator is log b. And if I now split this into two terms, then you'd get that y must equal log a by log b plus log b by log b, which is 1. Right? And now to calculate y, all I need to do is substitute this ratio. But we have the inverse of the ratio over here. So what I can do is I can do 1 by this and substitute it here. If I do that, this becomes 1 by x minus 1 plus 1 as the value of y. So simply calculate. So this becomes 1 plus x minus 1 divided by x minus 1, and so the final answer would be x by x minus 1. So that's the required value. Y, the new logarithm, would be equal to x by x minus 1. I'll look for it in the options. Yes, I have option D as exactly the same. So there you go. That's how you manipulate logarithms, right? Now some of you will probably think, why take the base as 10? Why not straight away change the base to b? And you're right, you could actually do that, but you'll obviously need to be a little more skilled with logarithms. So for example, if I start with this and I apply the change of base, right? So this becomes log ab divided by log a when expressed in the base b. And so this will become log a in the base b plus log b in the base b divided by log a in the base b, right, as the value of x. Now it turns out this is 1. Sorry, this value will be 1. So this value of x basically becomes, and let's say we denote this as t. So x would be t plus 1 divided by t. Or you can calculate the value of t by cross multiplying and manipulating. You'd get t as 1 by x minus 1. So I have this, I'm going to use this somewhere to substitute for log a in the base b. Let's go back to the next expression. What do I want? I want the value of y as log of ab divided in the base of b. So if I use the addition rule, then this becomes log a plus log b expressed in the same base b. And now log a in the base b we've already assumed as t, which means this becomes t plus 1. And so if I substitute the value of t, this becomes 1 by x minus 1 plus 1, and you can see very neatly that this becomes 1 plus x minus 1 divided by x minus 1, which is nothing but x by x minus 1. That's the same answer, option D. Right? So many ways that you could have manipulated this expression, all of which are right. I guess it all depends on how comfortable you are with the logarithm, with the properties of logarithms. Alright, here's another one. As ever, I would really recommend that you pause the video if you're watching a recording and solve it yourself, and then come back and see the solution. So here log x plus another log is equal to 6, and we want to find the value of x, right? So you tend to notice that these two have different powers, the different bases, but 4 is, the other base 2 when raised to the second power, right? So this basically becomes log of x in the base of 2 square plus log of x in the base 2, and we know when the base contains a power, the power comes out in the denominators, which means this becomes half log of x in the base 2 plus log of x in the base 2 is equal to 6. So I can take log x as common. This becomes log of x in the base 2 in common, and from the first term I have 1 by 2 left, and from the second term I have nothing, so 1 equal to 6, right? And so 1 by 2 plus 1 is 3 by 2, which means log of x in the base 2 would be nothing but 6 divided by 3 by 2, that's 6 into 2 by 3. What is this? This is 4. So if log of x in the base 2 is indeed equal to 4, what would x be? Take an anti-log. At this stage, take an anti-log, right? So 2 raised to the power 4 would then be equal to x. So x is equal to 2 power 4, which is 16. Right? So there you go. That's how you calculate x as 16. Option D again, the answer, correct answer in this question. Right? So you can see that, slowly and steadily I'm using more of the properties, the limited set of properties that we've learned, but we're applying it in a variety of situations and problem types. Okay, here's another one. So log of 27 in the base 12 is given as a, then how do we find the log of 16 in the base of 6, right? Notice again the relationship between the bases. Here you have 3 cube, here you have 2 to the power 4. Okay, so one has the radicand as a power of 3 and radicand as a power of 2, and here I have the base as 2 square into 3, 4 into 3, 12. Here my base is 2 into 3, right? So both the power, both the radicand as well as the base contain either 2's or 3's or a combination of them, right? So which immediately tells me, in order to sort of simplify it, why not put all of this together in another base, in a base which is common and constant and fixed. So I can see that again, change of base, right? Because these logs are in different bases, why don't I convert them into a base that is common to both expressions? So I apply a change of base. I want to change the base to something which is common, maybe the common log, base 10. So if I change the base to 10, in the first expression, a would then be log 27 upon log 12, right? And log 27 is 3 cube, which means this will become 3 log 3 divided by log 12. I know that's 2 square into 3, so since they're getting multiplied, you can split them up into 2 logs which are getting added, and the first log that gets added is 2 square. So log 2 square will be 2 log 2, and log 3 would come as it is, right? So this is what I have. A is equal to 3 log 3 by 2 log 2 plus log 3. Whereas the second expression which I want to calculate, let me now call it B. So if I start calling it B, then I'll say B, which I need to calculate, is equal to, by change of base, this will become log 16 divided by log 6, which is 2 into 3. Yeah. So this becomes 16 is 2 to the power 4, so that becomes 4 log 2 divided by log 2 plus log 3. So this is what I get. Now how do I use this expression and determine the next expression? Well, the answer in a nutshell is, notice what is similar in both expressions. Both expressions contain log 2 and log 3, and these logarithms occur in the numerator and the denominator. So maybe I should convert them into a single value, which I can then calculate. So here's the hint. You want to express this in terms of a single value that I can then determine. So what I do is I divide this expression by log 3. You want to divide this by log 3. What happens? So A would then equal 3 log 3, that's 3, divided by 2 times log 2 by log 3, plus log 3 by log 3, which would be 1. Right? And if I substitute this expression as t, this becomes 3 by 2t plus 1 equal to a. And immediately I can cross multiply and calculate the value of a, which basically gives me, let me multiply this right up here. 3 will be 2ta plus a, and since I want the value of t, that would be equal to 3 minus a divided by 2a, right? So I have the value of t, which I know is nothing but log 2 by log 3, and in the expression for b, now I do the same thing. I divide. You do the same thing. You divide this by log 3. So what does this become? This becomes 4 times. Numerator becomes log 2 by log 3, and the denominator will become log 2 by log 3 plus log 3 by log 3, which is 1. Right? So this basically turns out this is 4t divided by t plus 1. And if I substitute the value of t, this becomes 4 times 3 minus a divided by 2a divided by 3 minus a divided by 2a plus 1, right? And all I need to do is now simplify it. I can see that the 2a, after you take an LCM, it will cancel out. So what will I be left with? Just the numerators. So that's 12 minus 4a divided by 3 minus a plus 2a. So this basically is 12 minus 4a divided by 3 plus a, right? That's the required expression. Do I find that here in the option choices? Yes. 4, if you take common, this becomes 4 times 3 minus a, and the denominator is 3 plus a. So again, the answer for this question 2 is option D. Yeah. So how did I, evaluate? I wrote the expressions as 2 different logs in the base, in a common base 10, and then we, from the first expression, we convert it into a fraction whose value we can determine and substitute into the second expression, also after dividing it by log 3. Yeah. So I hope this question is clear to all. It's a slightly tricky one, but I hope that you get, you are getting an understanding of this. So recap. We did some basic questions where all we needed to do was apply the antilog property. Then we moved on to some problems where, which were applications of the other, basic properties that we had. And finally now we've come to problems where expressions containing logarithms are being manipulated, so that, one given logarithmic expression can be used as a basis to calculate another logarithmic expression. Both the previous question as well as this one, was of that variety, right? Okay, let's move on. Here's another type, right? By way, we need to combine various expressions, but the logarithm is not really written in it. Right? A is equal to b power x, b is equal to c power y, c is equal to a power z, right? And I want the value of x, y, z. So to calculate the powers, right, to bring the power outside, you take a logarithm. You take log on both sides. What happens? So log a would be log b power x, which is x log b, which means x would be log a by log b. Similarly, if you take a logarithm with this, you get log b is equal to y log c. The power will come out, and so y would be equal to log b by log c. You can sort of sense what's going to happen here. If I take a logarithm in the third expression, that gives me log c is equal to z times log a, and that means that z would be log c divided by log a. And since the question asked me the value of x, y, z, we'll say x into y into z would be equal to log a by log b into log b by log c into log c by, this is log a divided by log a, right? And you can see log a will get knocked off, log b also gets cancelled, so does log c, so the required product must be equal to 1. That's option C here. I hope that makes sense to you guys. If you didn't use the logarithm here, this question is a little hard to solve. But logarithm makes this question a matter of 3-4 steps. Go on. Here's another type of question, right, where we actually deal with common logarithms and find values. Right? So if this is one of the basic problems. If log 2 is given, log 2 common log, so I omit the base 0.3010. How do I find log 5? Right? Now with such problems, it's usually very, very common to consider the first 2-3 properties, right, which basically say that when is the logarithm equal to 1? When the base and the radicand is the same. Similarly, when is the logarithm equal to 0? When the radicand is 1, right? So we don't really need the second property here, but we will make use of the first, right? And you write this down and immediately it sort of hits you to your face that, oh, this 10 is nothing but the product of this 2 and this 5. Right? So I can then write this as log of 2 times 5 is 1, and using the additive property, this becomes log 2 plus log 5 equals 1. And if I substitute the value of log 2, I'll get the value of log 5 as 1 minus log 2, that's 1 minus 0.3010, and so the answer is going to be 0. 10 minus 0, 9, 9 and 6. So 0.6990, that's option C. There are many such manipulations that can happen. So for example, let me give you a variation right here. If the question had said, given log 2, calculate for me the value of log 0.04. And there are many ways of doing this. You'll say, okay, I want log of 4 by 100, which would be log a by b. Using the division rule, you'll say log 4 minus log 100, right? And now the base comes into play, because when the base is 10 and this is 2 square, the power will come out. This becomes 2 log 2, and what power of 10 makes 100? The second power. So this becomes 2 times log 2's value is 3.010 minus 2. So this gives me 0.6020 minus 2, and hence the value of the logarithm would be minus, let me subtract, minus 1.3980. That's the required logarithm, 0.04. Yeah. Okay, let's look at some other variations, right? So here you can see log 3 is given to me, log 7 is also given to me, and we wish to find the value of log 23 1/3. Seemingly doesn't contain any 7. In fact, doesn't even contain 3. It contains 3 in the denominator, but nowhere else. That's funny. So how do I deal with this? So what you do is, you want to write this as log. First convert the mixed fraction into a improper fraction. 23 into 369 plus 170. So this becomes log 70 by 3. And log a by b will be log a minus log b. In fact, I could probably write this as log 7 into 10 divided by 3. So which means this would become log 7 plus log 10 minus log 3. So that, using the given values, log 7 is 0.84. In fact, I could directly stack this up like this: 0.8451 plus log 10 is 10 in the base 10. So what power of 10 makes 10? The first power, plus 1. Yeah, so that becomes 1.8451, and from this I need to subtract the value of log 3, right? So that's 0.4771. So if you subtract 0.4771, and you get the difference, right? 15 minus 7, 8, 13 minus 7, 6, 7 minus 4, 3, and so 1.3680, and there you go. Option A here is the correct choice. So I hope that you guys are grasping this. It's if you ask me, not a very, very hard problem, but it's definitely a type of problem which comes with practice. You get better at this with practice. Let me clear up this page. Move on to the next question. Log 2 is given. Okay, here's slightly, remember I started off with logarithms and I said the common logarithm is actually an indicator of the number of digits in the number, right? So if log 2 indeed is 0.3, notice that the value of the logarithm lies between 0 and 1, which means it will have how many digits? The integer portion of the number will have one more than 1, which means it will have 2 digits. Sorry, one more than 0, which means it will have a single digit. Right? And we're talking about the radicand here. So indeed radicand has a single digit. Anyhow, as an aside, how do I calculate the number of digits in a given exponent? Right? So we'll say, okay, let the exponent be 2 to the power 64. I want the number of digits in this exponent. So we use logarithms here. You take a log, common log n in the base 10 would be log of 64, would be the log of 2 raised to the power 64. You know that the power comes out, so this becomes 64 times log 2, and so log n would then be 64 times 0.30103, right? So I'm going to quickly sort of calculate this up top. 0.30103 into 64. 64 into 3 is 192. So 2 and then 99, 1 carry. 64 1 the 64 plus 165, and the 64 into 3 is 192. And I need to put 5 decimal places. So this becomes 19.26592. Okay, but you don't want the value of the logarithm, you want the value of n, right? So now you take an antilog, right? So basically the sequence of steps is that first you take a log and then you take an antilog, right? If you take an antilog, remember we're working with a base of 10. So this becomes n equals 10 to the power 19.26592. Now we want to get some idea about n from the way it's written as a power of 10, right? So now the rule here says that whatever you get as the power, you look at the integer portion and you increment it with 1, and that should be the number of digits. So the rule here, you can remember it as a shortcut. If you come across this question, then at the final step after you take a log and an antilog, all you need to do is increment the integer part by 1, and that will be the final answer. But why? Right? Why is that so? Right? Well, the explanation is quite simple. The explanation is that if you write this as 10 power 19 plus 0.26592, then this can split into 10 power 0.26592 into 10 power 19, right? Now what does 10 power 19 do? It shifts the decimal 19 places. Correct? Which means, you'll have the first part which is not an integer, which probably has a lot of digits in the decimal, but 10 power 19 will make sure that it takes that decimal point and it shifts it to the right. So next thing I need to do is I need to figure out what about 10 to the power 0.26592, right? So to figure that out, here's what we do, right? You basically try and compare the power 0.26592. It lies between 0 and 1, and the logarithmic expression in the base of 10 is an increasing logarithm, which means and so is the exponential function. So 10 power 0 must also be smaller than 10 power 0.26592, which in turn must be less than 10 power 1. What does that mean? It means that this portion, the first portion of this expression, so this expression, the first portion here, basically is a value which lies between 10 power 0, which itself is 1, and 10 power 1, which itself is 0, which itself is 10. Yeah, let me sort of use a different colored pen so you can understand what I mean. So this portion of the number will be equal to 1, and this limit, the other end, will be equal to 10, right? So what we understand is that this value must lie between 1 and 10, right? So basically this value will contain decimal digits, but the integer portion, since it's greater than 1 but less than 10, it will be definitely 2 point something or 3 point something or something like that. And it will have a single digit in the integer and then many digits in the decimal part. And then I take this number and I shift its decimal 19 places. So from having a single integer place, it will now contain 20 digits on the integer side, right? So when I do this, how many digits do I get in the integer? I get 20, right? Now you'll also think that, but then there must be some digits left in the decimal. What about those? Well, you circle back to the original value of n. Remember, this was an expression of n, wasn't it? So you look at the value of n, which is an exponent in a base of 2 with the power as an integer. So 2 to the power 64 is definitely an integer, right? So once we circle back, to this expression and we say, okay, you'll get 20 digits in the decimal, on the integer side, you can also simultaneously conclude that will take away any decimal digit that must have come about, because this is an integer value, so it must not have any decimal digits. So the answer must be the 20 digits that we finally ended up with, right? So answer is 20, right? So the logic is that whenever you have n as equal to 10 to the power a plus b, right, where b is lying between 0 and 1, then you will say this number will have a plus 1 digits. Okay, something is going wrong, please excuse me for that. So if you have 10 power a plus b where b lies between 0 and 1, you can directly conclude that this will have a plus 1 digits. Yeah. Just keep that in mind when you're dealing with these kind of problems, that the number of digits, all you need to do is do a log and an anti-log. You'll get the number in the form of 10 power something, and you look at the integer part of that power and increment it by 1, you'll get the final answer. Right? So that's what you do when you're dealing with problems about the number of digits in an exponent. Alright, on that note, I'm going to leave you with this question. I want you guys to try this yourself. I'll be back in just a minute. Take a bathroom break. I'll be back. Hello again. So we're back, and I hope that you guys managed to get this question, managed to solve this question in fact. So here's what we do. We're given log 2, we're given log 3, we want the number of digits in this exponent, 6 power 20. So we start with n, let's say is 6 to the power of 20. So take a log, first step, log n. Common log would be log of 6 power 20, which would be 20 times log of 6, and in fact this will be 20 times log of 2 plus log of 3. Why is that? Because 6 itself is the product of 2 and 3. Okay, so we got here so far. I can then substitute the values given, 0.30103 plus 0.47712, right? So if I add, right, let me just add it here, 30103. So this becomes 5, 1, 8, 7 and 7. Okay, so I have 0.78815. I need to multiply this with 20. Let me also do that here. Right? So now I'll leave the 0 untouched. 2 5s are 10, 2 1 2 plus 1 3, 16, 14 plus 1 15 and 15. Right? And then I'll put a 0 at the end, and I'll say 5 decimal places will take me to 15.563. So this becomes, in fact, I'll start it here. N now becomes log of n now becomes 15.563, and the very next step would be n would then be 10 raised to the power, taking an anti-log. Step number 2, perform the anti-log operation, right? So if you perform the anti-log operation, this becomes, n would then be equal to 10 to the power 15.563. And I told you last, that whenever you have 10 to the power something, you look at the integer portion and you increment it by 1, and this would give me 16 as the number of digits in n, which means the number of digits in this exponent 6 power 20 would be 16. So I hope you have a measure of this method, the approach. The approach works when you're dealing with exponents, and although you need the value of a common log to manipulate. Okay, here's my, here's the 20th problem, which actually is a question that came in the CAT, and this question uses a different property. We've all along been using one property, the additive, or the multiplicative, or the change of base property, but here we use a different property, which is, remember the last property, exponent to the an expression containing an exponent and a log, x to the power log y. Now can be, what you can do is you can swap the power, the base and the radicand, right? So this can also be written as y to the power of log of x, right? And I start thinking about this property the moment I look at this question, because it contains an exponent whose base is b, and then the power of that exponent contains a log, right? So whenever you have a exponent containing log in the power, we use this property, right? So in that property you can swap the base and the radicand. So first I'm going to write this as 2x into b raised to the power. I'll take the 4 inside the log. That becomes b raised to the power log of x raised to the power 4 when the base is b equals 486, right? And I can obviously knock the 0 divided by 2. This becomes 243. So and now if I apply that property, x into, and I can swap these two things, the base and the radicand. So this becomes into x power 4 whole raised to the power of log b in the base b, and this equals 243. So what does that mean? Log b in the base b, when the radicand and the base is the same, the logarithm value will be 1, which means this becomes x into x power 4 is equal to 243. On the left hand side I have adding the powers becomes 5. On the right hand side 243 is itself 3 power 5, which means x must be 3. Perfect, that's the right answer. That's option A. By the way, I think this was one of the questions that came in a previous edition of the CAT. So you can see that it's a direct application of one of the properties, but I introduced this late in the day so that you guys first become comfortable with the basic ones. Alright, now having dealt with logarithms, you'll find it easier, much easier actually to work with exponents. Let's go ahead and take a quick look at the basic properties of exponents. We've in fact been using most of these properties. An exponential function is a to the power of x, where the base a, just like in a logarithm, a must be positive and a can never be equal to 1, right? I think this is a good time to quickly also tell you about the graphs for the graph of log of x and the graph of the exponent function. Or in fact, let me introduce that in just a while. I know that I will bring that up, but just not right away. So the first thing we've learned here is that fx, the logarithmic, the exponential function is of the form a power x, base must be positive and not equal to 1. Obviously, when the value of x a power 0, any exponent raised to the 0th power would be equal to 1. Any exponent raised to a negative power, in fact, the reciprocal of a power m. And when the power of an exponent is a fraction, then think of it as the root. Right? So three very simple sort of operations that we will perform. Three very, very simple operations that we will perform when the power is 0, or the power is negative, or the power is a fraction. You should know that the exponent becomes 1 or a fraction, or the rest, that is the reciprocal, or the root of m. Just like the additive rule of logs, you have the additive rule of exponents. When you multiply exponents, their powers get added. When you divide exponents, their powers get subtracted. and when you raise an exponent to another power, their powers get multiplied. So you have the additive rule, the multiplication rule, and the product rule. Addition rule, subtraction rule, and the multiplicative rule for both logarithms as well as exponents. And in fact, since we know one is the inverse of other, it's no surprise that these properties sort of mirror each other. And finally, if you have two exponents with the same power, you can actually multiply their bases, and even the reverse is true, right? And in fact, we use the reverse all the time. So if I have 15 to the power 7, then we tend to write this as 3 into 5 raised to the power 7, and that can be then split into 3 to the power 7 into 5 to the power 7. Can you see that this is exactly the same property, right? AB to the power of A power m into B power m is in fact equal to AB raised to the same power m. Okay, a problem on application of these properties for exponents. Let's take a look at this question. Find the value of x from the given equation, right? You can see this has a power of 6 and this is a reciprocal of a power of 6, which means you can write this expression as 6 times x square plus 3x equals 1 by 36. Reciprocal is negative power and the denominator has the power of 2, so this would be 6 power minus 2, right? And when two exponents are the same base, the powers would be equal. So x square plus 3x would be equal to minus 2, which means x square plus 3x plus 2 equals 0. And you can very easily factorize the quadratic into x plus 1 into x plus 2. So what do I get? Either that x is negative minus 1 or that x can be minus 2, right? So what are the possible values of x? I'm getting both minus 1 and minus 2 as possible values of x. It's a very straightforward question. Let's try to apply this on another question, right? Another problem dealing with exponents. So you can see here that you have 2 into an exponent with base as 4. This itself should give you a clue. Why not write this as 2 square and 8 in fact as 2 cube, right? So that's what I'll do. So beginning, first step, I'll say 2 times 2 square to the power x plus 1 equals 4, which is 2 square, into 2 cube raised to the power x plus 2. Right? And so, using the properties of exponents, here you have, you have a multiplication rule. So this becomes 2 power 1 into 2 power 2x plus 2. Here you have 2 power 2 into 2 to the power 3x plus 6. And again, adding these powers, this becomes 2 power 2x plus 3 equal to 2 to the power 3x plus 6 plus 2, that's 3x plus 8, right? And since the bases are the same, you'll say that the powers should be equal. So 2x power plus 3 should be equal to 3x plus 8, which means that x would be equal to 5, right? And that's x would be equal to, 3 minus 5, that's minus 5, right? That's option A over here. Yeah. So again, a simple problem, right? How about this question? 9 to the power of something minus 81 to the power of something. You can see both of them are powers of 3. But in fact, both of them are not just powers of 3, they are also powers of 9, right? So why choose a smaller power if you can use a bigger power? So I'll retain 9. I'll write this as 9 to the power 2x minus 1 minus 9 square to the power of x minus 1 equals 1944. So this becomes 9 power 2x minus 1 minus 9 power 2x minus 2. Right? So you notice that 2x minus 1 and 2x minus 2, right? So, here's the trick, right? You can write 2x minus 2, the power here, as 2x minus 1, the previous power, minus 1. Right? Or the other way around, you could write 2x minus 1 as 2x minus 2 plus 1, right? And why do I do this, right? Think about it. How will that help me? What will that achieve for me? Well, look at this. Let's try and apply it and we'll start to see the light. So if I replace 2x minus 1 from this expression, this becomes 9 to the power 2x minus 2 plus 1 minus 9 power 2x minus 2 is equal to 1944, right? And so if I use the addition rule here, this becomes 9 power 2x minus 2 into 9 minus 9 power 2x minus 2 equal to 1944, right? And 9 power 2x minus 2 can now be taken in common, right? That's the advantage. So I have 9 in the first expression, the second one would be 1 equal to 1944. This is 8, so I can very confidently say it should cancel out. 8 2s are 16, 34, 8 4s are 32, 2, 24, 8 3s are 24. So 243 is in fact 3 to the power 5. So at this point I'm going to express 9 as 3 square to the power 2x minus 2, which means the power will end up becoming 4x minus 4, and the power here is equal to 5, which means x would be equal to 9 by 4. And so that's your final answer, 9 upon 4. Is that then the options? Yes, indeed, that's option B. So the correct choice is option B, 9 by 4, which is the value of x. So little more time consuming, a slightly counterintuitive step that we took, but one that comes with practice and with having dealt with exponents and logs before. That's definitely an operation which you would think of performing. Alright, so let me move on to the next question. Here's another question. Just as usual, if you haven't, if you're not watching this live, then maybe you could pause and try this question yourself. So what do I have? I have an expression containing powers of 2, 3, 2, 3, 2. So powers of 2 and 3 on the left, and 3, 2, 2. So powers of 2 and 3 on the right. So clearly, maybe I could combine them all into single, bases. Not multiple bases, but multiply. So I'm going to write each of them, as 2 power. This is 2 power 19, but this is 2 power half raised to the power 19. And then I have 3 power 4, and 4 square is 2 square whole square. 8 is 2 cube raised to the power n equals 3 power n into 16, which is 2 power 4 raised to the power m, and 64 is 2 power 6, but then we have the 4th root, so this divided by into raised to the power 1 by 4. So what do I get? If I combine powers of 2 together, here you have 19 by 2, and then you are adding 2 square. 2 into 2 is 4, and finally you are also adding 3n. I'll also combine powers of 3. There is nothing else here, so 4. But on the right hand side, 3 power n into 2 to the power what? 4m plus 6 by 4. Right? That's 3 by 2. So equating the powers of 2 and 3 respectively, you'd say 3n plus, what is this? 8, 19 plus 8 is 27 by 2 should be equal to 4m plus 3 by 2. And equating powers of 3, you'd say n is equal to 4. Right? Now n is equal to 4, substitute that here and get the value of m. So I'll get, if n is 4, this will be 12 plus 27 by 2 minus 3 by 2. So 27 minus 3 whole divided by 2 is equal to 4m. Right? So what do I get for m? This is 12 plus 24 by 2 is 12. You would have noticed this. This is 4 square, but this is 9 power m, and I have not written that here. Right? So I have missed out an entire term. So let me include that. Right? So I have excluded 3 square to the power of m, which means this will become 3 power 4 plus 2m, right? So 4 plus 2m would then equal the value of n, right? And I'll probably substitute that in the other expression. Instead of putting n as 4, I'll put n in terms of m, and we will solve the other equation, right? So let's try doing that now. So if you substitute the value of n, you'll get 3 times 2m plus 4 plus 27 by 2 would equal 4m plus 3 by 2. Right? So you'll get 3 times 2, 6, and you'll bring the 4m here. So 6m minus 4m would then be 3 minus 27 whole divided by 2, because both of these have denominators as 2, minus 3 4s are 12 minus 12. Right? So I'm getting 2m as equal to minus 24 by 2, that's minus 12, minus 12, which means m should be equal to minus 24 divided by 2, that's minus 12. So the answer to this question is option C, minus 12. Alright, I think I have a question or two more from exponents. Let's look at this one. Again, it's it looks quite similar to the previous one, previous question we solved. I need to manipulate and express everything in terms of 2 and 3. So left hand side becomes 2 to the power, that remains the same. So we'll in fact only work with probably the right hand side. So here I'll write this as 2 cube. 6 is 2 into 3, so this will be 2 power half into 3 power half divided by 27, which is 3 power minus 3. So then this basically becomes 2 power 3 plus half, so 3 and a half, and 3 power 0.5 minus 3, that's minus 2 and a half. Right? And if I then equate the powers, you'll get the first equation as 0.7x the power of 2 should equal 3.5. That gives me the value of x as 35 by 7, 5, and minus 1.25y the power of y should equal minus 2.5, right? And so you can see that y would be 2, right? So I'm getting x equal to 5, y is equal to 2, that's option D. Sorry, that's option E. But why do we need the other expression? Well, actually you don't. You really don't need that. But we can probably quickly check. What is 4 power 0.3x? That's 4 power 0.3 into 5. That's 1.5. Right? That's like 2 square to the power 3 by 2. That becomes 2 cube, which is 8. Yes, that's exactly what I'm supposed to get. And similarly, right hand side, and the other power 9 power 0.2 into y, that's 0.2 into 2.4. So that's 3 square to the power. So we want to write it in terms of 81. That's 3 square to the power 0.4, which means that's 3 to the power 0.8. And if I try and manipulate this, 81 to the power 1 by 5 is like 3 power 4 raised to the power 1 by 5. That's like 3 power 4 by 5, which is 0.8, right? So indeed these two are also equal. So you don't really need the second equation. It's actually redundant. You could have marked option E as the right choice by using the first equation itself. Okay, here's another question. This came in the CAT, I think last year or so. N and x are positive integers such that n power n is 2 power 160. Okay, this is itself a very interesting expression, right? I want to manipulate this, the power and the base, so that both become equal, right? So I can try. So obviously 2 square to the power 80. No, that doesn't work because this is 4 to the power 80. I can also write this as, I can't write this as 2 cubes, so 2 power 4 to the power 4 into 40 is 160, so this becomes 16 to the power 40, not of much use either. 2 power 5 maybe, raised to the power what? 5 into 32 is 160, so this is voila, 32 to the power 32, right? So if n to the power n is 32 to the power 32, clearly n must be 32. and let's use that in the second expression. This is an integral multiple of, not 2x, 2 power x. So n square, that's like 32 square plus 2 power n, that's 2 power 32, is an integer multiple. So it should be some number x, let's not take x, let's say 8 into 2 raised to the power x. So what is the biggest value that x can take? Okay. So you basically want to simplify this with powers of 2. So this is 2 power 5, 5 2s are 10, plus 2 power 32. And so what can I write this as? I can take 2 power 10 as common. If you don't understand that, you can write this as 2 power 10 plus 2 power 10 plus 22, which means this is like 2 power 10 plus 2 power 10 into 2 power 22, which basically means that the given expression 32 square plus 2 to power 32 can be written as 2 power 10 into 1 plus 2 power 22. Now clearly this number is not divisible by 2. It's still an integer, but it's not divisible by 2, right? So which means the maximum powers I can extract would be 2 power 10. So the largest possible value of x should be actually 10, right? And it's a very simple question, but it's not so straightforward, it's not so basic either, because we needed to manipulate and find the right way of expressing n power n or 32 power 32, 2 power 160 in a appropriate manner, and that takes a little bit of hit and trial. Okay, and then we come to the final sort of question type. So far we were dealing with only sort of basic properties in equations, but then logs and exponents can also feature in inequalities, and so you need, besides knowing the basic properties, when dealing with inequalities, there's one other nuance that you need to know, which is that these two functions, the logarithmic function and the exponent function, there's a property called, is the function monotonically increasing or decreasing, right? Which means if I keep increasing the value of the independent variable x, does that increase the function or does that decrease the function? Right? Well, for a logarithmic function or an exponential function, I can take a set of very simple examples, but before I start giving you the examples, I'll show you the graphs, right? And the graphs are one way of you visualizing and understanding these properties. So the graph for a power x looks like this. It's a continuously increasing curve. It increases from 0. Remember, the y coordinate increases from 0 and goes all the way to infinity, right? So this is the graph for a power x versus x. But this is the graph when a is greater than 1. If indeed a were less than 1, then the graph changes. It will look like this. This is the graph for a power x versus x when a lies between 0 and 1. So the curve is increasing if a is greater than 1, right? You can remember it that way. And the curve is decreasing when a lies between 0 and 1. And here's where I think taking some values and understanding, will help you, will make things a little clearer. So for example, if I consider, 2 to the power of x, instead of, so if y is 2 to the power x, so take increasing values of x, right? If you put x as 0, I'll get y as 1. If you put x as 1, I'll get y as 2. If you put x as 2, y will become 3, right? In fact, here you were increasing. What if you were to decrease? What if I put minus 1? So 2 power minus 1 is 1 by 2, that's 0.5. So this x has reduced, so has y. If I reduce it further, I put minus 2. So this will be 2 power minus 2, that's 1 by 2 square, that's 1 by 4, that's 0.25. Again it's reduced, right? So when x increases, y increases. When x decreases, y also decreases. This kind of a function is called an increasing function. Right? In a sense, if you take a point where the function is of greater value and you compare with another point where the function value is decreasing, then the value of x will also decrease. Or conversely, if the function value increases, and that would mean that the independent, the power x for the exponent will also increase. Right? So that's what the increasing function means. But this behavior is different if the function y were something like 0.1 to the power x. Right? I take a base which is less than 1, between 0 and 1. And now what happens if you substitute different values of x and compare the values of corresponding values of y? So if I put 0, I'll get 1. But if I increase the value of x, I put x as 1, I'll get 0.1. You can see y is reduced. If I increase it further, right, x as 2, 0.1 square is 0.01. It's reduced further. What if I decrease x, right? If I put x as minus 1, so this will be 0.1 to the power minus 1, that's 1 by 0.1, that's actually equal to 10. So you can see decreasing this increases the function value, right? And decreasing it further, this will become 0.1 square, 0.1 to the power minus 2, that's 1 by 0.1 square, that's 1 by 0.01, that's 100. You can see how it behaves, right? When I decrease y, x seems to have increased, and when I increase y, then x seems to have decreased, right? And that's what the graph also tells you, right? If you consider, 2 or more points where the function value has reduced, it has fallen, you can see that the value of x would have increased, right? So while y has reduced, x has increased, or conversely, if y increases, then x will reduce. So that's the increasing versus decreasing function type. So the exponent function can be both increasing or decreasing, and no surprises, so will the logarithmic function, right? The logarithmic function also behaves in a similar manner. I can show you the graph, you can try some values yourself and try and check this out. But the logarithmic function looks like this. It's an increasing function, log of x versus x will be an increasing function when the base a is greater than 1. Right? You can see it increasing, right? On the other hand, if the base were less than 1, then the graph of log of x in the base of a would actually be a decreasing curve. Right? So I don't know if you guys like working with graphs, but if ever you can get confused and you just remember the graph, you can also figure out from the graph. Here's how. Let me show you how. So if I remember that these are the two graphs for a greater than 1 and a less than 1, right? So then I'll look at any 2 points on the curve, and I'll say, okay, this is the point which is higher, this is the point which is lower, and so clearly y has increased from here to here, but corresponding function value has also increased from here to here. So here you'll say this is an increasing function type. But if I choose 2 points in this curve, right, and measure their function values, you can see function value increases from the lower point to the upper point, but from the lower point to the upper point, the value of the radicand has actually decreased. So here they move in opposite direction. So this is a decreasing function type. Right? So that's the treatment or the understanding that maybe the graph gives you. If you can remember that will be well and fine. Alternatively, you can think that the log or the exponents are increasing when their base is greater than 1. Which means if the function value log or the exponent value increases, then x must have increased, and they are decreasing when a lies between 0 and 1, which means if the logarithm increases, then x would have reduced. If the exponent a power x has decreased, then x might have increased. So it moves in the opposite direction. Right? And these properties have been tabulated here, slightly different manner. So it says in the exponent function, if a power m is greater than n, a power m is greater than a power n, then your conclusion with a as constant will depend on the value of a. You'll say if a is greater than 1, I know it's an increasing function, so the greater value will have the greater power. But if a lies between 0 and 1, then it's a decreasing function type, so the greater value of the exponent a power m will have a smaller power, right? So m would be smaller than n, right? So that's one other way in which you can probably state this. Ditto for the logarithmic function. If one logarithm is greater than the other, so if the base is greater than 1, we know it's increasing, so the bigger logarithm value will have the bigger radical, m will be greater than n. But if the base lies between 0 and 1, then the bigger then they move in opposite direction, which means that the bigger logarithm will have the smaller radical. So m will be smaller than n if a were between 0 and 1. Right? So these are useful properties. You will tend to pick them up if you come across inequalities containing logs and exponents. Okay? And let's look at that. So here you go. Log of something is less than 1, right? So the moment I know that this is an expression which is less than 1, I should think, why not first express this as a log? And we know that log of, when the base and the radicand are same, the logarithm is equal to 1. So I'll choose the base as 2. So this becomes 1 becomes log 2 in the base 2. Right? So I'll use that logic and rewrite the expression as log in the base 2 of 3x minus 1 divided by 2 minus x must be less than log of 2. Right? Now since the base 2 is greater than 1, we know it's an increasing function type. And if it's an increasing logarithmic function, then the logarithm will have the greater radicand, right? So here you'll say inequality sign remains exactly the same. So 3x minus 1 by 2 minus x must be greater than 2. You can in fact, then it's a question of solving the inequality. You bring the inequality to the left. But before you go ahead and solve it, right? Besides the radicand being greater, right? Besides using the fact that the smaller logarithm will have the smaller radicand, you say the condition is also that the logarithm must exist. And when does the logarithm exist? When 3x minus 1 by 2 minus x, the radicand is positive. So the radicand must be positive but greater than 2. Yeah, which is kind of redundant, because if it's positive, then it must be greater than 2, right? Or the other way around, if it's greater than 2, then it must be greater than 0. But don't think about that. Sort of just use these two conditions. I'll manipulate the first one by bringing the 2 to the left hand side. This basically becomes 3x minus 1 minus 2 times 2, 4 plus x divided by 2 minus x is greater than 2, and 3x minus 1 by 2 minus x is greater than 0, right? What we're trying to do is factorize it to get the critical point. So what do I get? 3x plus x, 4x minus minus 5 divided by 2 minus x is greater than 0, and 3x minus 1 divided by 2 minus x is greater than 0, right? So this is these are the conditions I get. For each of these inequalities, you can observe the critical points. Here the critical point numerator will have 5 by 4 as the critical point, denominator will have x equal to 2 as the critical point. In the other inequality, you'll have the critical points as x equal to 1 by 3 and x equal to 2. Right? So if I go back with the standard approach for inequalities is to use the number line and to plot these critical points. So what I'll do is that I'll plot first the left hand side inequality, that maybe I'll use different colors for both, right? So I'll use the white color for the first inequality. So the critical points are 5 by 4 and 2, and the second inequality besides 5 by 4 has a critical point as 1 by 3, right? So I can see that the number line is split up into these 3 regions, these 4 regions rather, right? But ideally you should be working on it one at a time. So let's work with the inequality to the left first. The critical points will be 4 by 5 and 2 minus x, right? So I'll for now ignore 1 by 3. I'll focus on 5 by 4 and 2 as critical points, right? So with inequalities, the general tendency is to try and put some values. Put x equal to 0 here. If you put x equal to 0 in the first one, you would get minus 5 divided by 2. You get a negative value, right? So x equal to 0 is over here somewhere, and I know that is negative, which means the next region will be positive, and the region after that will alternate and become negative, right? So minus plus minus. So the correct region is the greater than 0 region. So we'll say okay. So then this means that the solution is that x lies in this range. Open at 5 by 4 and 2, it has to be lying between 5 by 4 and 2. And okay, I just noticed that I have made a little bit of a blunder. This is not greater than, increasing would mean that this remains the same inequality sign, which is less than. So this would then be less than 2, and this would then be less than 0. So you don't want the, you don't want the positive region, you actually want the negative region. So everything up until that point is fine, but I'll choose the negative region and say, okay, the solution set will be x should be less than 5 by 4 or x should be greater than 2. Okay, inequality 1 solved. Let's work with the other inequality. I'm going to take a different colored pen so you'll understand now I'm working with the second inequality. So the critical points are 1 by 3 and 2. I already have 1 by 3 over here. I have 2 over here. These are now the the 2 regions which I will get. Let's again plug origin. F of 0, right, in this expression becomes minus 1 divided by 2, right, which is still a positive, still a negative value. So here 2 negative, and then between the 2 regions positive, and then next region it will be negative, right? Maybe I should put the positive side over here, right? And for this inequality we want the greater than equal to 0 side. We want the positive region, right? So the positive region we plot by again enclosing it within this region. So I'll put a open block here and open here. So this is my solution, right? And since both need to be true, we want to find what is the common region, right? So you want the region that is common to both, right? And where do we get that region? Well, you can see that here both solutions, both straight lines exist. Obviously nothing here because the white line exists but not the red. Here the red line exists. Here the red line exists but not the white, and here the white exists but not the red. So the only solution region would be this open region, which is x lies between 1 by 3 and 2. I'm quickly sort of checking whether I seem to be in a mood to make plenty of silly mistakes. So and indeed I have made one. a terrible one at that. You can see that, when you subtract, it will be minus 2x, minus of minus 2x will be 2x. So this becomes 5x minus 5, which means the critical point will not be 5 by 4, it will in fact be 5 by 5, which is 1. Right? So this point won't be 5 by 4, it will in fact be 1. Right? Everything else remains the same, but this point is 1. So my solution will be x lies between, x lies between 1 by 3 and 1. Right? 1 by 3 to 1 is option A. So the answer to this question is option A. By solving the two inequalities, one which we got directly and the second by applying a constraint to the base, you will see that the common region that emanates from these two conditions will be the final answer. Right? It's a tough question, it's a tricky question, and one where I made a lot of silly mistakes, but jokes apart, the process is not very hard. You need to know how to work with inequalities and you need to know your logarithms or exponents. Right? If you know both of these well enough, it's not a very hard question. You should be able to stitch them together. Right? So I'll leave it to your judgment whether you should be attempting this or not. I will, however, show you one more problem of a similar nature. Here's the question. Right? You can see that this is, instead of a log, it contains exponents now, right? And 0.343 is in fact 0.343 is in fact 0.7 cube, right? But you will notice that the base is 0.7 here, which means the base is less than 1. And when the base is less than 1, you say that the function must be a decreasing function, which means that when the function decreases, the power increases, x increases. So here the function has decreased because this is less than this. So you must reverse the inequality, right, when it deals with the powers. So you say, so 2x square minus 3x plus 4 must be greater than 3, right? Or 2x square minus 3x plus 1 is greater than 0. Right? You can factorize this as 2x minus 1 into x minus 1. 2x square minus 2x minus x plus 1, yes. Right? Which basically will give me the critical points of 1 by 2 and 1. And again, if I make the regions, and I'll say, okay, let's check f of 0 origin, I'm getting as positive plus 1, right? So origin is on the left hand side, less than 1 by 2, origin is positive, this region would be negative and this region would be positive. So my answer to this question would be x less than 1 by 2 or x greater than 1. So less than 1 by 2 and greater than 1 sounds correct, but the last condition we did not check is that the power should not be, but it turns out that there is no problem with the power. The second condition that we used in the previous question, for example, was to do with the radical, right? But here with an exponent, there is no constraint on the radical. The power, right? The power of an exponent can be positive, it can be negative, it can be 0, it can be anything you want it to be, right? So here, this is the only condition. My correct answer here would be the option D. Sorry for that. Would be option D. Yeah. So this one is much easier because you had to deal with only one inequality. This might not always be the case, but be careful. Okay, with that, my discussion on logarithms and modulus sort of comes to an end. I have tried to sort of discuss the most basic properties all the way till application level problems on exponents and logarithms. By no means is this list exhaustive, but I think I've broadly covered most of the important ones, right? The ones that are most likely to come, the kind of properties that are most likely to be used have been covered in today's session. do try these questions yourself all over again after a break of a day or two, and do practice in more questions from logarithms, because that's the only way that you get better and confident and accurate at logarithms. Right? On that note, I will circle back and tell you that this session was brought to you by Unacademy. Unacademy is one of India's largest learning platforms. It is in fact the largest learning platform currently, helping students out for CAT and various management exams. And if you haven't tried Unacademy out, guys, then you're really missing out on something great, because not only does it give you a great way of interacting with your faculty and asking doubts and solving tests and quizzes, it is also brilliant because it gives you great amount of flexibility. Now, sometime back I told you it gives you flexibility on whom should I study from. There are so many educators, I get to pick. In fact, I don't need to pick one, I can pick one for every topic for that matter. Right? But it also gives you flexibility in choosing what language you want to study in, what platform, what device do you want to study with, what kind of a schedule should I be following. Should I study in the mornings? Should I study in the afternoon? Should I study at night? Should I study on weekdays? Should I study on weekends? Right? So it gives you this, infinite amount of flexibility, which should suit every one of you who's watching this video. The other obvious thing is that I think I've said this before, but it's very, very critical when you're studying for CAT or any management exam. You need to interact with the mentor. It cannot be one-way communication, because that way then your doubts remain unresolved. You can't always learn by watching recorded lectures. You need to go live. And when you're live, the Unacademy platform is simply superb, right? In today's session, for example, I'm sure most of you are watching this live, but when you try this on the Unacademy platform, you can post questions and they come at real time to the faculty. So, which means that you will stop me midway when I'm solving a question and ask me, sir, I think I have a problem with this step, or you can probably point out that maybe I made a silly mistake or two. But we keep each other on our toes, and that's a big advantage that Unacademy gives you. I think there is a new feature also that Unacademy has recently launched, which has to do with quiz, conducting live quizzes, right? And so this is a great way of taking learning and making it not just interactive but also interesting, right? And so the point I'm trying to drive at is that if you haven't tried out Unacademy, the app, if you haven't downloaded the app and attended a few free sessions there, what we call as special classes on the platform, then you're really missing out on something, guys. Because there's so many free classes happening. I think take some as trial and try and experience how the platform works before you start to upgrade, right? And I'll tell you why you should be upgrading. And one of the big reasons why you should be upgrading is that you get access to a different category of educators. You get access to their same educators who take special classes, but they run a lot more structured programs and batches when it comes to Plus. So you can upgrade for that reason. Number two, all the platform's features are now visible to you, which means you can start practicing. You can start taking practice tests on the same platform, which means not only do you learn, you also diagnose and practice and analyze your performance on the same platform. So that also comes your way when you upgrade to a Plus course. And finally, I think one big advantage is that all the lectures that you attend on Plus, the educator notes, for example, this presentation that I shared with you today, with all the properties and the questions and all the annotations, every single bit can be downloaded by you in the form of PDFs, right? So the class notes are available with the educator's annotations, and you can download this and it becomes your personal notebook, your personal learning material. So that's also a big advantage for why you should be upgrading to Plus. When you're upgrading, there are many available plans. You can see that these plans are short-term plans for 1 month all the way to long-term plans for a year or two. And my simple recommendation is always choose long-term plans, right? Always choose something which is either a year or 2 years, because what you're doing is you're giving yourself, the extra added benefit for longer duration, but at very, very little cost, because you can see that the increment is cost is very marginal, but the increment is value is stupendous. You almost double your validity by simply adding maybe about 20% of the 25% of the cost. So register and subscribe. I mean, first try the app out now, and then I'm sure you're gonna love it. At that stage, upgrade to Plus, and don't remember to use my referral code. That's AV01. Anand Venkatesan. If you like this session, then remember Anand Venkatesan taught you logarithms and exponents. So AV001 is my referral code, and if you use my referral code, you get a 10% off straight away when you buy a subscription plan, right? So keep that in mind. On that note, that's my time, guys. Thanks a lot. I hope that you guys like this session. Do give me your critical comments on the on this video. Do mention whether you liked it or not. If you want something different, or how I can make this better in the comment section. But I assure you, one way or the other, together we will crack the cat. If you like this video, do press the like button, do share and subscribe this in your amongst your friend circles. It would do me a favor of a bit of good. But thank you. Have a great day. And I have another class coming up today on YouTube on the same channel. That's at 4:30 p.m. So if you can find the time, do join me at 4:30. We deal with algebra there. We deal with circles today. So try and join me there. And all of next week I will also be taking a lot of special classes on weekdays. I think except for Tuesday I should be available on the Unacademy app every single day at 3 p.m. So if you want to see me on the Educator app, on the Unacademy app, then log in on any weekday, download the app and see my class, follow my class, attend my class there at 3 p.m. right? That's my slot. All right, thank you, have a great day, and I'll catch you guys very, very soon. Bye bye.